Okay, let's just dive right into it. Welcome to this insider playbook on mastering packet transmission between hosts in different topologies. In today's explainer, we're going to treat your Cambridge 9618 computer science exam answers exactly like a master architect treats a blueprint. Because frankly, that's what's required. Whether you're currently laying the groundwork with foundational IGCSE IT frameworks, or you're scaling all the way up to our main focus today, the AS and A-Level 9618 syllabus, the ultimate goal is exactly the same. We want every single paragraph you write to be a structural masterpiece. No weak foundations, no missing load-bearing walls, just perfectly constructed answers.
So you might be wondering, why do so many students lose easy, predictable marks on packet transmission? Honestly, it's a tragedy to watch. You've studied the textbooks, right? You know what a router is. You know exactly what a packet header contains. But then you sit down, you look at an actual past paper scenario, and the marks just completely slip away. And here is the secret. Most students lose easy marks here not because they don't know the computer science facts. They lose them because they don't understand the architectural strategy of the exam itself. They aren't playing the game the way the examiner wants them to play it. Well, by utilizing the specific strategy we are breaking down today, you absolutely won't be one of those students. We're going to pull back the curtain and show you exactly what the principal examiners are desperately looking for.
Here's our roadmap for today's session. Phase 1, the foundation and core principles. Phase 2, the method mark strategy. Phase 3, evaluating algorithm quality. And finally, Phase 4, top examiner warnings pulled straight from the official Cambridge reports. Let's get right into it. Part 1. The foundation and core principles. I want you to notice the distinct ways these two hypothetical candidates completely fail the exact same question. Look over at Alex's approach. Alex overloads the answer with raw computer science facts. We're talking a complete data dump. Alex writes down absolutely everything they've ever memorized about TCP/IP, IP addresses, MAC addresses, you name it. But here's the fatal flaw. Alex completely ignores the specific star topology network that was actually mentioned in the prompt. There's literally zero analysis of how the central switch in that exact scenario processes those packets. Now look at Sam's approach. Sam rushes and totally misses the command word requirements. If the examiner's command word is evaluate, Sam just describes. Evaluate means you need to weigh the pros and cons, but Sam just gives a basic definition. Both of these students lose massive marks because they completely ignore the Peel framework. You know it. Point, evidence, explanation, and link. Elite students use Peel to explicitly answer the prompt they are given, not the prompt they wish they were given. If you just regurgitate raw facts like Alex, or if you ignore the command words like Sam, your architectural blueprint collapses instantly. To actually build out that Peel structure, you have to start with your vocabulary. And this brings us to a massive, flashing red terminology alert. The explicit warning from examiners year after year is crystal clear. Candidates consistently confuse key terminology. You absolutely must define your terms first. Think about it. If you were going to write a whole paragraph about a gateway, translating protocols between dissimilar networks, or you're going to talk about a subnet mask, identifying the network portion of an IP address during packet transmission, you cannot just drop those words in and hope the examiner assumes you know what they mean. You need to define what those terms mean, specifically in the context of the question, before you deploy them in your extended responses. Define your terms clearly, and you secure those foundational knowledge marks immediately. And this right here brilliantly illustrates the difference between an average candidate and an elite candidate. A poor approach relies entirely on isolated, siloed facts, but the top approach, it thrives on cross-topic connections. The Cambridge syllabus heavily emphasizes that high-performing students exhibit a connected, conceptual understanding of the subject. Let me give you an example. If you're discussing packet transmission, don't just awkwardly stick to the networking chapter. Branch out. Bring in data representation. Talk about how the packet header is actually formatted in binary or hexadecimal. Bring in hardware. Explain how the physical network interface cards, the NICs, actually process that incoming data stream. Candidates who actively weave in these cross-topic connections achieve significantly higher marks because their blueprint is fully integrated. They show they understand the whole system, not just one isolated part of it. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Part 2. The method mark strategy. Systematic processing within packet transmission follows a very strict standardized 5-step sequence. Step 1.
Identify key elements. What exactly is the source, what is the destination, and what specific topologies are involved in this network? Step 2. Apply relevant principles. For instance, are we dealing with CSMA/CD protocols to handle potential packet collisions? Step 3. Execute your analysis with crystal clear working. You need to show the exact path the packet takes, step by step, hop by hop. Step 4. Verify your results. Take a step back and ask, does this path make logical sense given the physical constraints of the network? And finally, Step 5. Present in the appropriate format. If the question asks for a diagram, draw the diagram. If it asks for a structured list, write a list. By laying out your working logically, you are extracting the core trend from incredibly complex data sources. And most importantly, you are scooping up vital method marks along the way, even if your final conclusion has a slight mathematical error. Process is everything. Now let's take that exact same logic and apply it to programming and algorithmic thinking. Practical application in packet transmission is how you develop your programming skills and secure those crucial high-tier method marks. The sequence here is straightforward. Design algorithms, implement solutions, test thoroughly, and evaluate performance. Imagine you are asked to write pseudocode for a dynamic routing protocol across a massive mesh topology. You need to show the examiner that you understand this exact life cycle. Designing the algorithm? That is your point and your evidence. Testing it and evaluating things like hop counts or path efficiency, that represents the explanation and link phases of your PLL framework. It all connects back to structure. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Part 3. Evaluating Algorithm Quality.
Okay, I'm going to challenge you right now. Do a quick 60-second mental data scan of these 3 critical factors: time complexity, space complexity, and edge cases. I want you to think about how these strictly and directly affect network performance during packet transmission. Think about time complexity. It dictates how fast a dynamic routing algorithm, let's say Dijkstra's shortest path algorithm, can actually calculate the optimal route before a packet just drops entirely. Then there's space complexity. This dictates how much physical memory the routing table actually requires on the router itself. If the table is too big, the router crashes. And what about edge cases? This is where students always lose marks. What happens if a critical link goes down in a ring topology versus a central node failing in a star topology? What happens during a massive, unexpected packet collision storm? Top-scoring candidates don't just define these terms, they constantly evaluate these exact real-world trade-offs in their answers.
The truly crucial point here is applying this critical analysis framework while you are sweating under exam time pressure. Step 1. Deconstruct the given info. Break the messy network scenario down into logical nodes and physical links. Step 2. Solve systematically. Apply the routing logic step by step without skipping ahead. Step 3. Evaluate for reasonableness. This one is huge. Look, if your algorithm accidentally calculates that a packet should bounce back and forth between 2 routers infinitely in a never-ending routing loop, you haven't checked for reasonableness. A packet can't live forever. That's why the time-to-live field exists. This exact deconstruct, solve, evaluate method is what Cambridge examiners are literally begging to see in your extended answers. Let's do a quick find the flaw exercise right now. Imagine you are stressed and you write this theoretical paragraph in your exam. The packet is sent from host A to host B. The router uses an IP address to find the destination. This is good because IP addresses are unique. Therefore, the packet arrives safely. Can you spot the flaw there? Where exactly did this stray from our PEL structure? Well, the major flaw is that the explanation and the link to the specific context are incredibly undeniably weak. It's way too generic. Sure, you made a point, but there is absolutely no evidence of how the router processes the network prefix in the packet header. There is no explanation of how the network's topology impacts the hop count, and there is zero link back to the specific constraints mentioned in the question prompt. You built an empty building with absolutely no architectural support. It's going to crumble under the examiner's red pen.
Part 4. Top examiner warnings and avoiding catastrophic mistakes.
Let's meticulously break down the top 3 catastrophic errors pulled directly from the official principal examiner reports. First, using the wrong formula or algorithm for the context. You absolutely cannot use a broadcast algorithm meant for a shared bus topology when the exam question clearly outlines a point-to-point mesh topology. They operate completely differently. Second, forgetting to check boundary conditions and edge cases. You have to ask yourself, what is the maximum bandwidth load this specific network can handle before packet loss occurs? What happens at the extreme limits of the packet size or the time-to-live fields we just talked about? And third, providing answers that are not specific to the context. I'm talking about writing perfectly memorized, beautifully written textbook paragraphs that have absolutely nothing to do with the actual scenario the paper provided. It's right answer, wrong question.
I want you to listen to this exact quote from the examiners. It's the most important thing you'll hear today. Answers must be specific to the context given in the question. This is the golden rule of the 9618 syllabus. If the scenario on the page is about a hospital transmitting encrypted patient data packets to an off-site laboratory, you must reference the hospital, the lab, and the specific security or topology constraints mentioned in that exact network. If you just spit out a generic, copy-pasted answer about the 7 layers of the OSI model, you are going to get 0 marks. Every single paragraph you write must be a structural masterpiece designed specifically for the ground it is built on.
So, here is your final cheat sheet recap. Combining these 3 distinct rules guarantees top marks. Rule 1. Command word decoding. You need to know exactly, mathematically, what words like evaluate, describe, explain, and compare demand of you. Rule 2. Peel framework application. Point, evidence, explanation, link. Never ever leave a technical point unsupported in the wind. Rule 3. Time management matrix. Allocate your exam time based strictly on the marks available and use that deconstruct, solve, evaluate method so you don't get bogged down in a panicked raw data dump.
And the payoff for this structured, architectural approach? It's massive. On average, students who transition from just dumping facts on a page to writing targeted, context-specific peel paragraphs see an improvement of 2 full grade boundaries. Let that sink in. That is the literal difference between a C and an A, just from changing your structural approach.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.